So welcome to Weeknights at the Wagner by the Wagner Free Institute of Science. This is our digital talk series. I'm Susan Glassman. I'm the director of the Wagner, and I'm delighted to have you join us for tonight's talk, Confronting Coastal Risk in an Age of Rising Sea Levels with Robert Kopp. This was originally scheduled to happen earlier this year at the Wagner, and we are really grateful to Bob Kopp for rescheduling and being willing to be part of this new for us online series. And as I said, especially given the weather, we're really glad that we're online. So briefly, a few words about the Wagner and just a few program logistics. The Wagner Free Institute of Science, for those of you who are new to us, is a natural history museum and educational institution that's located in Philadelphia. We were founded in 1855, and we have a mission to teach contemporary science to the public. We also interpret and preserve our historic building, which is a time capsule of 19th century science. You can sort of see it in the picture behind me. Tonight's talk is just one of many programs we offer, but as it says in our name, our programs are free to make them accessible to everyone. We occupy a National Landmark building with a museum, a library, and a historic lecture hall, which is where our programs normally take place. While we've been closed for the pandemic, we've adapted our programs to offer them remotely. And we are currently offering all of our courses and lectures and science lessons and museum tours online, so you can access them from home. Tonight is part of our Weeknights at the Wagner series. It's been happening bi-weekly on Wednesdays, each with a different speaker. This is the last one. We're winding up 2020. We've been able to make our talks available on YouTube channel, on our Facebook, so you can catch up on any of those you might have missed earlier this year. We'll be offering all of our courses and programs online for the winter and into the spring most likely as well. They'll start up again in late January, early February. We'll be announcing them after the holidays. If you're interested in staying connected with the Wagner, you can sign up for a newsletter or hook up with us through Facebook, Instagram, or Twitter. So now I am delighted to welcome Dr. Robert Kopp. He is a climate scientist and serves at Rutgers University as the director of Rutgers Institute of Earth, Ocean, and Atmospheric Sciences. He's also a professor there in the Department of Earth and Planetary Sciences. He co-directs Rutgers' Transdisciplinary Coastal Climate Risk and Resilience Initiative, which brings graduate students in fields across natural and social sciences, engineering, and urban planning together with stakeholders to tackle the challenges that climate change poses to the world's coastlines, which of course is somewhat what he'll talk about tonight. He's also director of the Climate Impact Lab, a multi-institutional collaboration that brings big data approaches to assess the economic risks of climate change. His research focuses on understanding uncertainty in past and future climate change with emphasis on sea level change. He's authored more than 90 scientific papers and also written many popular articles, and is a lead author of the Intergovernmental Panel on Climate Change's forthcoming sixth assessment report, and also worked on the US Global Change Research Program's 2017 Fourth National Climate Assessment. So he is very well versed in this. And then just one last quick plug for the Wagner. As I said, everything we do is pretty much free of charge. We rely on donations, but it's our mission to make science widely accessible by being free. And it's something we've been doing for 165 years. We've managed to adapt these programs really for the first time to make them online, available online while our building's closed, but it's challenging and we need some support. So if you enjoy the program tonight, which we know you will, and would like to see more, please consider making a donation to our annual appeal. We have a really ambitious goal to finish this year out so we can start 2021 strong, and we have a matching gift that we're trying to raise $20,000 for. So every gift that comes in will be doubled. Everyone who's contributed, we thank you. What we do is not possible without support, and we're grateful. So now I'm going to turn the program over to Bob Kopp. Thank you for coming and doing this program.
Thank you, Susan. And thanks to almost 300 of you for virtually braving the snow to show up tonight. This is certainly a much larger audience than we would have gotten if we were trying to do it in person, and I'm glad you're here. Now, I think as you all know, we are living in a time of rapid environmental change, and that change has created what fits to the nose the definition of a global crisis, right? With crisis being a point when decisions are being made that is going to set the course of a phenomenon, a disease, a global transformation for generations to come. And so tonight, I want to zero in on one particular element of the global climate crisis, namely that associated with sea level rise. And I'm going to take both a global and a somewhat local perspective. I'm going to draw to some extent on local examples from here, what I expect is nearby for many of you in New Jersey, to talk about what's going on. So first, the big global picture. For over 800,000 years, carbon dioxide concentrations in the atmosphere stayed between about 180 parts per million during cold periods that we call ice ages, and about 300 parts per million during warmer periods that we call interglacial periods. And this was the level to around 300 parts per million, around 280 parts per million. This is what carbon dioxide concentrations were in the early 19th century. In 1913, as a result of the combustion of fossil fuels primarily, carbon dioxide concentrations surpassed 300 parts per million. And in spring 2014, they surpassed 400 parts per million for the first time, probably in at least 2 or 3 million years. I'm going to just show you an 800,000 year sweep of history. If we zoom in on the last 250 some years, you can see this in a little more detail. In 1750, before the invention of the steam engine, carbon dioxide concentrations were around 277 parts per million. Over the next century, with the start of the Industrial Revolution, they rose about 10 parts per million. Over the next 50 years, they rose about another 10 parts per million. Over the next 50 years, they rose about 15 parts per million. That gets us up to right after World War II. Between 1950 and 1988, global carbon dioxide concentrations rose another 40 parts per million. And 1988 is a significant year because it is, among other things, the time of the first congressional hearings on climate change. And so it can be viewed as sort of a turning point on our civic understanding of what we were doing to the atmosphere. Since that time, carbon dioxide concentrations have gone up about over 60 parts per million. I think this year we're around 414 parts per million. And so the key thing to realize is that most of this increase has happened since the mid-1980s, right? I'm a geologist by training. I tend to take the long view. I tend to think of carbon dioxide and global climate change as a phenomenon of the Industrial Revolution, and it certainly is. But to a very real extent, it's a phenomenon of the post-Cold War era, the same era that has seen rising inequality in the US, the same era that has seen a variety of governance challenges nationally. All of these phenomena are happening together. And why has most of the carbon dioxide increase happened since 1988? It's because most of the fossil carbon dioxide ever emitted into the atmosphere has been emitted since 1988. So this plot here is showing you from 1750 to around 2018, the total cumulative amount of fossil carbon dioxide emitted by different countries. So that means, for instance, if you look at the number at the end, these numbers are everything emitted from the start of the Industrial Revolution to, let's say this is 2018. And so what you see is, well, 1750, we were at 0 billion tons, gigatons is a billion tons emitted. Over the next century, we emitted about 5 billion tons. Over the next 50 years, we emitted another 40 billion tons, bringing the cumulative amount emitted between 1750 and 1900 to about 45 billion tons, which is roughly as much as we now emit in a single year. Between 1900 and 1950, cumulative emissions rose to 230 billion tons. By 1988, they were at 750 billion tons. And by 2019, they were at 1,610 billion tons. So again, most of the fossil carbon dioxide ever emitted has been emitted since the end of the Cold War, frankly, and since the first congressional hearings on climate change. And as a result of this emission of carbon dioxide and of physics that has been well studied since the late 19th century, our planet is running a fever. This plot here is showing you NASA estimates of global average surface temperature, where 0 is the average over the last 20 years of the 19th century. And what you see is that there has been this gradual increase, but the real rapid increase started around 1980. And between 1980 and 2018, global temperatures have risen at an average rate of about 0.2 degrees Celsius or 0.3 degrees Fahrenheit per decade, leading to a global average temperature in 2018 that was about 1.1 degrees Celsius above the late 19th century average, or 2 degrees Fahrenheit. The last 5 years, and this is probably going to always be true for many decades to come, the last 5 years are most likely the warmest 5 on record. And if we zoom in, I promised you a little bit of a local look. Temperatures are rising in the mid-Atlantic US faster than the global average. These are statewide average temperatures for New Jersey, from my colleagues at Rutgers at the State Climatologist Office. And in New Jersey, average annual temperature is now nearly 2 degrees Celsius, about 3.4 degrees Fahrenheit higher than in the early 1900s. So this is largely going to be a sea level talk. So how is sea level changing today? Well, since the early 1990s, scientists have measured the changes in the height of the sea surface using satellite-borne radars, measured by satellites like this one. This is a JASON-3 satellite. And there was a new satellite launched this year that continues this mission. And what you see from studying the satellite record is that sea level is rising at quite different rates in different places. So this is a map from the 4th National Climate Assessment is showing you the change in the height of the sea surface from 1993 to 2015, so over about 20 years. And you can see, first of all, the warm colors are indicating areas where the sea surface height has risen. The blue areas are where it's fallen. And so one point to take away is that the fact that sea level is rising as a whole doesn't mean it's rising everywhere. And you see a lot of variability that has to do with things like the circulation of the atmosphere and the ocean. So phenomena like El Nino and longer term counterparts to that have a significant effect when we look on these timescales. But despite all that variability, the global trend is clear. Global average sea level is rising, and it's rising at an accelerating rate. So this is what the different interpretations of the satellite record show you. If you take a global map and average them together to get global average sea level, in the early 1990s, global average sea level was rising about 1 inch per decade. In the last decade, it's been rising at closer to about 1.5 inches per decade. And for longer context, we don't have to rely on the satellite record. We can turn to both instrumental observations, so tide gauges, which have been placed around the world, some of the oldest ones dating to the 18th century, but most of them for the last 60 years or 70 years or so, which are basically just sticks in the ground that measure how high the water is above the stick. And going back further, we can use the geological record, which is an area that some of my colleagues at Rutgers and students at Rutgers and colleagues around the world are focused on. Use the geological record to reconstruct longer term records of sea level. So over here on the left, this is an example of a salt marsh where some of my collaborators have reconstructed a record of past sea level going back about 3,000 years. Over here on the right is the tide gauge, where the tide gauge station is in the Battery in the southern tip of Manhattan. If we piece that together, we can get a curve of sea level going back over 3,000 years. And the punchline from this analysis, which Barack Obama tweeted about when we first came up with it in 2016, is that we are seeing the fastest rate in sea levels, rise in sea levels in nearly 3,000 years. And in fact, new data since then can show that we are very conclusively seeing the fastest rate in over 3,000 years. So that's the global picture. The ocean is, like temperature, ocean is rising even faster along the mid-Atlantic US than in the global average. So here is a figure from a report that we did for the New Jersey Department of Environmental Protection last year. So these are tide gauge records of sea level. So from 1910 to 2020, the black curve is global average sea level. The orange curve is New York City. The green curve is Atlantic City. Since 1911, sea level in coastal New Jersey has risen by about 1.5 feet, which is about 10 inches more than the global average. And this difference is largely due to two factors. One, the land is sinking because of natural reasons that have to do with where the ice sheets were in the last ice age. And that's what drives the difference between global average and New York in the long term. And then on top of that, on the Jersey Shore, because we're basically sitting on a pile of sand, we get an additional difference due to the subsidence of the land caused by pumping groundwater out of the land. So that's about another 3 inches over this time period. And as a result of these changes, we're seeing more and more impacts. So higher sea levels mean you need less extreme events to cause impactful flooding. Sea level rise is making high tide flooding more common. This is a photo from Ventnor, New Jersey, of a high tide flood. So, not a storm in the sky, just a clear day with an extremely high tide. And what we see is that the number of high tide flooding days in Atlantic City have increased from less than about 1 per year on average in the 1950s to an average of about 8 per year over the last decade, a period over which sea level rose locally by about 9 inches. And that's just the sort of more common floods. The same is true with larger floods driven by storms. You need less of a storm to cause the same amount of flooding, and you need you get more flooding from the same level of storm. So sea level rise and enhancing storm-driven flooding. Human-caused sea level rise was responsible, according to analyses we've done with our partners at Climate Central, based in Princeton, was responsible for about 18%, about $10 billion of the Sandy recovery costs in New York and New Jersey, and exposed about 100,000 people who wouldn't otherwise have been exposed to flooding during Hurricane Sandy. We can look at this in other ways. So this is some analysis we've done with colleagues at the Rhodium Group, Berkeley, and the University of Chicago. And this shows that if we look at the rate of annual flooding, about 27,000 more properties in New Jersey are flooding at least once a year than would have in the 1980s. And if you look at this plot, you can see they're largely concentrated in places like Cape May and Ocean and Atlantic in Monmouth County, the Jersey Shore counties, but there's also some on the Delaware Bay Shore. And again, the same phenomenon. We're seeing losses from hurricanes, average annual losses increasing by about $1 billion per year since the 1980s as a result of sea level rise. Again, concentrated in this case in the areas with the densest population and property in New Jersey. So this would be places like Hudson County. And if we just look at exposure, we'll find this that there is about 600,000 people in New Jersey, about 7% of the total state population, that live within about 10 feet of the high tide line. Areas that are potentially vulnerable to the effects of sea level rise and sea level rise amplified flooding over the next century. So these are areas that are home to about $200 billion of property in the state. So what is driving this change? So at a global level, shrinking ice sheets and glaciers are responsible for most of the 3 inches of global sea level rise that happened since 1993. This is a picture of Jakobshavn ice fjord in Greenland. And this is basically a cliff where the ice sheet is flowing out and then collapsing, and you get this pile up, what's called melange here. If we break this down a little, there are 3 main sources of ice that are melting. So there's the Greenland ice sheet, there's the Antarctic ice sheet, and then there's the mountain glaciers all over the world. So up here on the top, we have satellite images or satellite images of the changing mass of the ice sheet. So red is area where satellites that measure the gravitational field of the Earth show that the ice sheet is losing mass. The bluer colors are areas that are gaining mass, which is what you expect in a warmer atmosphere because you can get more precipitation and more intense snowfall. And so you see a lot of loss in Greenland. In Antarctica, we have this area of loss that's concentrated in this area around the Amundsen Sea. And Greenland has contributed about 0.5 inch to sea level rise since 1993, Antarctica about 0.3 inches. And then the mountain glaciers around the world, though they're smaller, have contributed the largest share, about 0.7 inches since 1993. But we're also can be concerned about this because if we just do an inventory of how much ice there is out there, there's potential for much larger sea level rise resulting from land ice loss. So if you just count up how much ice is in glaciers, there's roughly a foot of sea level rise that would happen globally if you were to mount all the mountain glaciers on the planet. If you were to mount all the Greenland ice sheet, and this is not something that's going to happen anytime soon, but could potentially happen over thousands of years, you're looking at around 23 feet of sea level rise. And if you look at the Antarctic ice sheet, again, not going to lose all of this in the next century, but the West Antarctic ice sheet, if you were to melt all of it, you get about 16 feet. The East Antarctic ice sheet, which has been there for tens of millions of years and is going to stick around for quite a long time, even in a very warm world, there's about 170 feet of sea level equivalent of ice locked up there. So if we start tabulating this, so roughly half of the global average sea level rise has happened, has been driven by ice melting over this time period. Most of the rest has been due to the fact that the ocean has been getting warmer. So roughly 40% is due to the ocean becoming less dense as it warms up. And then there's about a 10% effect that's due to changes in the amount of water stored on land. For instance, when we pump that groundwater out, not only does it cause local sinking, some of that water runs off into the ocean where it contributes to sea level rise. Now, that's the global average story. If we start looking at specific places, Philadelphia, the Jersey Shore, wherever you want, it becomes much more complex. It always does when you start looking in the local detail. So New Jersey, over the same time period, we've had not 3 inches, but about 4.8 inches of sea level rise. About 1.3 inches due to global expansion of the ocean as it warms up. About 2.3 inches are due to that sinking of the land, and largely due to the ongoing response to the fact that there were giant ice sheets not far north of us that were distorting the land and that we're still recovering from, and also due to the effect of subsidence driven by pumping of groundwater. And then there's a little 0.9 inches, a little bit less than the global average, that's due to ice melting. And that's because when you melt ice, these are huge masses, right? So to raise global average sea level by about 1/10 of an inch is almost 1 trillion tons of ice. That has an effect on Earth's gravity field and Earth's rotation. And so what that means is you actually get less sea level rise near a melting ice sheet or near a melting glacier than you do in the global average. And so rather than about 1.5 inch globally, we get about 0.9 inches from ice melting in New Jersey. And then there's about 0.3 inches that are due to other local factors, some combination of changes in land water storage and changes in circulation, so possibly some effects of Gulf Stream, some effects of changes of the wind. So it's a complicated picture, but this is the overall budget of what's going on here. So, okay, if that's what's going on, right now, what can we anticipate in the future? Well, to project future changes, we need to project all of these different processes we were just talking about. And I'll say, I'll get to your question at the end. Thank you for asking them. So we've developed a framework for doing this at Rutgers, which has been widely used, as I'll mention in a bit. And it basically involves combining different approaches for these different processes. So with the projections I'm about to show you, for vertical land motion, we sort of just learn what's happened over the last century and assume that continues to happen. That's a very good assumption. If we're looking at, say, the response to the last ice age, that's been going on for thousands of years. It's not going to change very quickly. It's a slightly more questionable assumption when we're talking about things like groundwater withdrawal, because groundwater withdrawal can change as a direct effect. But a good estimate is sort of it's going to do on average what it's done over the last century. For the global contribution of changes in water and dams and in groundwater, we've used an approach that looks at how changing population in the past has related to dam construction and has related to groundwater withdrawal. So for this middle portion, so how much the oceans expand when they warm up, how the winds change, how the currents change. That's where global climate models are strongest. And so they provide a key source of information there. And then, melting of ice on land, that is a sort of hard question. It's an area where the science is still rapidly developing. And so our approach here is to take a whole bunch of different approaches and look at what emerges from ice sheet models of different sorts, of ice sheet models that have different sorts of physics in them, as well as methods for sort of formally assessing expert judgment in a calibrated way. So this framework has been widely used in US stakeholder-driven assessment. We actually invented it originally because of some work we were doing doing a US economic risk assessment, but it turns out that when you provide local sea level projections, it turned out to be in high demand. So our approach has been used by Washington, Oregon, California, Maryland, Delaware, Boston, New Jersey, and is an important input into national climate assessment. And a key driver when we look at future projections is the range of possible human emissions. So this figure here is showing you global greenhouse gas emissions from 1990 through 2100 under different sorts of projections. So this gray projection here, I'm sorry, the gray projection here is basically what we would have called business as usual maybe 15 or 20 years ago. So this is what would happen if there were no transition away from fossil fuels, called baseline here. And that would leave you somewhere about 4 to 5 degrees Celsius of warming above pre-industrials. And if you aren't familiar with thinking in degrees Celsius, you should know that, right, the global temperature targets that all the nations of the world have agreed to are 2 degrees C or well below 2 degrees C and as close as possible to 1.5 degrees C. So this is far from that. These blue and light blue curves, that's an estimate of where current global policies would get us. So we're sort of on track for plateauing probably of global greenhouse gas emissions. This year was a year of rapid greenhouse gas emissions decline. Due to the effects of COVID, but it's one where that decline has been driven by sort of the crudest policy possible, right? So sort of slowing down the economy. And if we just go back to business as usual, to sort of what current policies are, we would stay on course for this sort of 3 degrees Celsius of warming. And these yellow and green curves represent pathways consistent with those 2 degree and 1.5 degree C targets. And note a couple of things. So the 1.5 degrees Celsius target, the most ambitious international target, that's pretty close to saying the decline in carbon dioxide emissions that happened this year needs to keep happening in a way that is much better for the economy. The yellow curve is a 2 degree C target. That 1.5 degree C target, notice that basically gets you to global net zero greenhouse gas emissions by around 2070, and carbon dioxide emissions in this world actually have to go to zero by about 2050. And then it goes negative afterwards. So that's a world where there's actually large-scale efforts to remove carbon dioxide from the atmosphere and remediate the climate. So this is a range of possible future emission spaces we want to think about when we're thinking of future sea level rise. Another key driver of the range of projections is that ice sheets are really complicated. Physics at a pretty local scale can have continental scale impacts. And so our understanding of ice sheets is rapidly evolving. There are physics that are sort of poorly understood and are only included in some models and not in other models. And so this is another key driver of the spread in sea level projection I'm about to show you, particularly in those higher emission worlds. Now, all that said, projecting sea level rise through the middle of the century is actually not that complicated. And it's not that sensitive to either emissions or ice sheet behavior. It's just these systems are slow moving, and there's, in the time scale of ice sheets and the time scales of the oceans, there's just not that much time between now and 2050. So this is some results from the analysis I mentioned earlier that we did for the New Jersey Department of Environmental Protection. So it's going to be a bunch of numbers I'm going to show you on the screen, and I apologize for that, but I think it actually is a helpful way of getting across. So let's walk through it. So these two columns are showing you 2030 and 2050, and these are sea level average relative to the year 2000. And 2010, for reference, was about 0.2 feet higher in New Jersey than the year 2000. And I can only show you 2010 and not 2020 because when we're talking about sea level in these terms, we're actually talking about a 2-decade average. So we don't know what the 2-decade average centered in 2020 is going to be yet. And so then the 5 rows are sort of indicating the range. And these think about like, how much are you willing to bet on different levels? So low in number, all of the different approaches we use for projecting sea level tell us there's at least a 95% chance, at least a 19 and 20 chance that we're going to be higher than this. High in numbers, all of the different approaches, all of the different treatments of the ice sheets tell us that we're going to be less, as a less than 5% chance will be above this, so less than 1 in 20 chance. And then this middle range is what we call the likely range. So there's at least a 2 in 3 chance we'll be in this likely range number. So 2030, we're likely looking at sea level in New Jersey about 0.5 to 1.1 feet higher than it was in the year 2000. 2050, likely between about 1 foot and 2 feet higher in New Jersey than it was in the year 2000. And we're pretty confident it's going to be more than 0.7 feet and less than 2.6 feet. That's the simple part. Once we start going beyond 2050, what I said before about the emissions and to some extent about the ice sheet behavior, that becomes increasingly less true. We can't do predictions anymore. We can only do projections based on different assumptions of how much we're going to emit over the future. So this is the full table from that report. So just to, we have now for the 3 time periods, 2070, 2100, and 2150, a low, moderate, and high emission scenario. So low is what we get if we're sort of consistent with the Paris Agreement. Moderate is what you get if we sort of stay roughly track current policies, but don't increase the level of ambition. And high is what we get in that if we somehow get back to the world of unchecked fossil emissions growth. Doesn't seem very likely we will get there. But we might also get to something that looks like that if there are feedbacks in the climate system that haven't been taken into account. But if we just focus on sort of the moderate emissions trajectory, where we're most likely headed right now, 2070, we're looking at about 1.5 to 3 feet. 2100, about 2 to 5 feet, with some possibility of as high as 7 feet. 2150, about 3 to 8 feet, some possibility as high as 14 feet. And then you can look at some of these other numbers. So if we compare the Paris Agreement goals, that trims the high in number from 7 feet to 5 feet. In 2100, it trims it from 14 feet to 8 feet in 2150. The other thing to take away is that sea level is going to rise beyond 2100, even if we're on a very ambitious emissions trajectory. So we have to prepare for sea level rise, even while we're trying to get from the blue column to the gold column. Now, this translates, as I already alluded to, into more frequent flooding. So this is for the moderate emissions scenario, showing you about how many of those flood events that are now happening about 8 days a year over the last decade, we expect to see in Atlantic City in a typical year. So by 2050, and this up to 2050, this is largely locked in, we're looking at a typical year probably seeing 45 to 255 days a year of high tide flooding. The sort, again, that happens about 10 days a year now, maybe 7, a little bit more than that. And that happened about 1 day per year in the 1950s. So this is a pretty substantial increase. And again, emphasizes the importance of managing this risk, not just by reducing emissions, but also by adapting the change. And then if we continue forward to 2100, under this moderate emission scenario, we're looking at 240 days per year to every day per year. If we look at hurricane risk, this is from that report we did with Rhodium Group that I mentioned earlier. About 90,000 properties worth about $80 billion will enter into the 1 in 30-year hurricane floodplain in New Jersey by 2050. Why focus on 1 in 30 years? That means basically you expect it to flood once during the typical mortgage lifetime. And here's just another way of thinking about this. So here we're looking at the number of extreme sea, or the frequency of extreme sea level events at Atlantic City. We're looking at the historic 10% probability extreme sea level events. So what historically in the year 2000 you would have expected to occur about once every 10 years on average. How does this change under a moderate emissions, middle of the road trajectory, which would get us to about 1.5 feet of sea level rise by 2050 and about 3.3 feet by 2100? Well, by 2030, that 1 in 10 year event has become the annual event. By 2055, you expect that 1 in 10 year event to be happening in about 5 to 10 days per year. By 2100, that's now the new permanent sea level. And if we happen to be at the high end of the projections, that moves everything up. So on the high end, by 2035, the 10-year event, 1 in 10 year event is now the 5 to 10 day a year event. By 2065 is now the new permanent sea level. So sounds challenging. We have to deal with it. We can't avoid dealing with the problem, even as we can try to limit it. So what do we do about it? Well, the first thing I want to impress upon you is that the consequences of our decisions often last longer than we might initially think. And this is an example I really like. This is a picture from the year 1911 of the relatively new Marion Power Station in Jersey City. It was built by the Public Service Electric Company in 1905. In the 1960s, it was replaced by the Hudson Generating Station, and the generating station closed in 2017. But that's not the end of the story, because power plants aren't just generators, they're nodes of the grid. And that grid topology, the way the grid is structured, outlasts the individual generator. This is a map from that Electric Railroad Journal, and I know it's fuzzy. I gather some people have been having trouble with fuzzy images in general, but this one just is fuzzy. This is a picture of the electric grid in New Jersey in 1911. This is a Marion switching station here, or the Hudson, the Marion generating station. The switching station there flooded in 2011 during Hurricane Irene and in 2012 during Hurricane Sandy. And again, it was sited in the first decade of the 20th century. In fact, if you look at the 14 PSE&G switching stations that flooded during Sandy, 7 of them you can find on this 1911 map of the electric grid. So it just goes to show, like, decisions made a century previously were affecting the vulnerability of the New Jersey electric grid in 2012. So what do we do? Well, option one is just to say, this is life. We should rebuild essentially unchanged. Maybe, in fact, when the floods come, we can get poor people to move out and we can gentrify the shore a little. And we just assume that this is going to be sustainable because right now this is subsidized by disaster relief and by flood insurance. And we can assume that continues indefinitely. As you can probably tell, this is not what I would consider the wisest approach to take or the most just. Do we accommodate? Do we modify our communities to accommodate occasional flooding? And this can take the physical form, example being housing elevation. This is a picture from Manasquan. It can take a social form, so improving evacuation routes and emergency communication. One thing we have to bear in mind is that this is not simply a personal decision, right? You can elevate your house if the infrastructure that supports you, that your sewer, your water lines aren't also protected against the flooding, and you decide to stay there, you could be stuck in your house during a flood without proper sewage, which is not great. Do we harden? Do we build defensive structures that try to reduce the risk of flooding? This is a illustration of the East Side Coastal Resiliency Project in Manhattan, which is a combination of berms, which you can sort of see here, and movable storm barriers to sort of effectively build either a literal wall or a temporary walls to keep the water out. But we have to remember, nothing is perfect. And so if we go for the hardened approach, we also have to have contingencies for when hard protection fails. And we also have to be aware of the fact that if you fail on your risk communication task, there may be people, and this happened to a whole bunch of people during Hurricane Harvey in the Houston area, who aren't aware of their flood risk. And so you get what's called the levee effect, where people can actually move into the area behind a barrier, increasing their vulnerability in the event that barrier fails. Do we expand protective natural infrastructure? This is an example of some oyster beds in Jamaica Bay. And these can be really useful for dampening wave energy and therefore the impacts of sort of short-lived high water events. They are not as, in general, as useful for sort of permanent flooding. So they can deal with the storm surge. They can't deal as well in general with just the water levels being overall higher. Or do we relocate? And this is an example from Oakwood Beach from Staten Island, which is a community neighborhood that took a buyout after Hurricane Sandy. And the answer is, well, we're going to need some combination of all of these. And what we probably don't want to do unless we are in a situation where we absolutely have to, is make the decision right now, because there is such that large range when we're looking at of potential sea levels when we're looking out beyond 2050. It would be foolish to ignore the high-end numbers. It would also be very costly and damaging to assume that those high-end numbers are going to happen. And so to the extent possible, the way thinking is going is moving towards what's called a flexible approach, flexible adaptation pathway. And this isn't simply sticking your head in the sand. This is very careful contingency planning, right? So it's understanding what the tools are that's available to your community, what levels of sea level rise they work for, and when you're going to switch from one set of tools, say, elevating changing regulations to encourage elevating houses, to another set of schools, say encouraging long-term relocation. And this is what this sort of diagram sometimes used in this is to indicate is like different strategies with different switching points between them. And the key thing I would argue is that you need to be having this discussion now. You need to know what your contingencies are. You shouldn't be planning as though the worst case is definitely going to happen, but you also can't ignore the worst case. Now, this is a great concept in practice, but to date, to our knowledge, these sorts of flexible approaches have largely been engineering driven. And so they've not considered, sort of the feedbacks with how humans make decisions and how we're going to respond. So like how the economy and demographics are going to shift. So you might see something like this in some of the more advanced Army Corps proposals that say, okay, well, when sea level rise gets to 1 feet, we need to implement these additional engineering measures. But really, this is something that needs to be viewed at a community level and not just as a technical Army Corps decision. The other challenge with these is that generally when they've been applied, they're considered financial costs, but not political economy, right? We can come up with a great contingency plan, but we also need to think carefully about who's going to implement that contingency plan and what the incentives are going to be when they have to make that additional decision. So there are serious institutional questions that require careful thought from social scientists and policy scholars about how to make sure that we can plan as a community and then actually follow through on those plans as we move forward. Now, one of the things we're working on at Rutgers is trying to do more science about climate change that is actually usable and successfully informed decision-making. And there's a few key traits that have been identified in the sustainable development literature about usable science that I think are useful for thinking of, that we try to hold as goals as we work on this. So one is credible, right? We got to provide communities we're working with scientifically adequate technical evidence and arguments, the best available science that we can provide. But you also have to be asking the right questions. There are some great fundamental research questions still to be answered about climate and ice sheets, but we need to make sure if we want to focus on the useful ones, we're doing ones that actually have implications, actually can help inform some of these decision makings. A third key element is legitimate, and this is something we've been working very hard on at Rutgers to train our students to do, as I'll mention in a minute. Basically, like in order to be legitimate, scientists have to come and listen. And I'm keeping an eye on the clock to make sure I have time to listen to you. But the challenge of active listening is very much a organizational side, and it requires a type of listening that doesn't necessarily come easily to a lot of scientists. And then finally, related to that is iterative, right? We're talking about ongoing dialogues between scientists and stakeholders. You cannot effectively do this if you just turn to a scientist, say, give us your best assessment, and then we'll run with it. Now, I want to mention that there's groups of organizations that are something called boundary organizations, where you have very skilled people who are working at this interface. Sometimes those are government agencies. So NOAA does a bunch of work in this area, but there's also other NGOs and that are very good at talking to both stakeholders and scientists. And I've really benefited at Rutgers from working with some wonderful people here who have this year, with support of the state, established what we call the New Jersey Climate Change Resource Center, which is a state-supported climate service that is drawing upon the power of the higher educational institutions of New Jersey to help inform municipal, state, and private decision makers as they work through the challenges of climate adaptation and climate change mitigation. The other thing that we also have to be cautious about is science can be usable, but it might not necessarily be used in a manner to promote just, equitable, and effective adaptation. And there are plenty of examples you can find where adaptation measures have happened in a way that do not advance the cause of justice. And there's a book on this that this is cited. The table has come from, many of these examples come from, say, Hurricane Katrina, where there's certainly been a major efforts to make the city more resilient, but in many cases, women or minority voices may not have been heard. Environmental standards have been relaxed. The benefits disproportionately benefit white, wealthy neighborhoods. And so when I talk to scientists, what I would say is you need to be sort of cognizant of the political economy at this level too. That usability for just, equitable, and effective adaptation may not be the same thing. And so to get back to what I'm trying to advance at Rutgers is expressed in this quote from a paper we wrote and published last year. We need to sort of dissolve the boundaries between the C-level scientists, the people working on the impacts, the social scientists, the decision makers, and the affected populations. All of these need to have a voice on the table. And yes, there's plenty of room for fundamental advances, whether they're inspired purely by curiosity or inspired by desire, by use, even when we're just talking about the physics of, say, how ice sheets respond. But we are really moving forward with, and we need to move forward with even more, training the next generation scientific workforce that works closely with non-specialists as a fundamental element, because we don't have time now with the climate crisis, for this disconnect between, the fundamental science over here and the challenges over here. We need to be doing the science that can effectively inform those challenges, and we need to be training scientists to do that. And as it happens, that's something we've been working at Rutgers over the last several years. We have a graduate training program that's been funded for the last 4 years by the National Science Foundation, called the Coastal Climate Risk and Resilience Initiative, and where we've been taking students who may come in through oceanography or geography or urban planning or engineering or ecology, and teach them to speak each other's languages, and importantly, to communicate with and listen to the people on the ground, and to work with coastal communities in developing resilience plans. And so just this week, our current cohort of students presented the resilience plan they developed with a couple of communities in Monmouth County, and some lessons they learned from that to the state. And I think this is a really exciting initiative, and I think it's really where a lot of the work in the climate science area needs to go. We definitely need the fundamental science, but we also really need to scale up our efforts to train people to work at this interface and to solve these problems, which are no longer problems for a distant future, but are really problems of today. And however we choose to adapt, I want to emphasize that the starting point is climate change mitigation. Right here, we're looking at a slightly different version of that plot I showed you earlier. This is now just through 2030. These are greenhouse gas emissions. The blue curve is that current policy trajectory headed towards 3 degrees Celsius in 2100. This is a 2-degree trajectory. This is the 1.5 degree trajectory. So that 1.5 degree trajectory sees global emissions basically cut in half by 2030. The 2 degree one sees them cut by about 20% by 2030. Regardless of emissions, New Jersey is likely to see about 1 to 2 feet of sea level rise between 2000 and 2050. But by the time we get to 2100, we are starting to see a significant difference, right? So under current emissions, we're likely looking at about 2 to 5 feet of sea level rise by 2100 with a high end of 7 feet. If we get on that 2 degree trajectory, we're looking at about 1.5 to 4 feet with the high end dropped from 7 feet to 5 feet. So that's a pretty significant reduction in that high end risk. So these big challenges, we need to talk, I want to hear what you have to say about it. And I hope some of you might want to work with us as Rutgers as we try to push this forward. Thanks.
Yeah. So there are a lot of questions, variety of things tracing your talk. But before I pitch those to you, one technical question that I'll just let everyone know is we do record the talk and it will be posted on our YouTube and Facebook channel. It will probably take us a couple of weeks. We have to close caption it, but for people who want to be able to go back at their leisure and watch it again, it will be posted. But one person asked through private chat whether the slides themselves could be made available. I don't know if that's something you're willing to do.
Yeah, we can do that, sure.
Okay, great. So we'll figure out a method for that. So onto the questions. I'm going back, scrolling through the beginning. One question was, is it possible that New York City land sinking has anything to do with all the buildings on the island?
So what I showed you for New York City was the battery, and the battery, no, that's on pretty solid, or the Southern Manhattan. It is not subsiding as a result of construction. That is basically just tracking the fact that the whole region is subsiding as a result of the fact that the ice sheets, when they were just to the north of us, pushed down the land underneath them and then caused a bulge on their edge. Just like if you push down on a mattress, you sort of get a bulge around the edge, and that bulge is now subsiding. That said, if you look at areas that are built on fill, those could be sinking as a result of building construction. There probably are parts of New York City that's not the battery tide gauge where that's a problem, but some of the biggest problem, if you look at places like Shanghai or Jakarta, this is a really very serious problem. I mean, or even parts of San Francisco, but it's a pretty local problem. The battery tide gauge I'm showing you is showing you sort of what the region as a whole is doing.
Any findings regarding the net estuarine, not a word I have to say often, marsh loss and growth in the face of subsidence and sea level rise?
That is a good question. I don't have like quantitative numbers for you. I could if you really wanted it, I can find somebody at Rutgers who could probably help. But broadly, one of the things sort of my co-authors and I have found is that there is a threshold rate of sea level rise around 7 millimeters per year. So about 20% faster than sea level is currently rising. Or sorry, I guess about 40% faster than sea level is currently rising in New Jersey. And if you stay below that, and there is enough supply of sediment and there's enough space, that marshes can basically keep up with sea level rise. If you go above that, generally they can't. And so we're sort of close to that threshold now. This is something where I think there's a good chance if we get on that low emissions trajectory, we could stay pretty close to that cutoff threshold. In New Jersey, if we're on a moderate or high emissions trajectory, I think we're very likely to overtop that 7 millimeters per year threshold.
So a number of people are asking questions about what's going to disappear. One of them was, will the barrier islands around Margate, Northern Liberties, I guess they mean in the Delaware, disappear in the 21st century?
So it depends. And I think what I say the best thing for you to do is probably to explore this yourself. There's a couple of tools you can use to do that. So one is the New Jersey Flood Mapper, if you just search for NJ Flood Mapper, or it's actually njfloodmapper.org. You can go and look at various water levels and see what floods at various water levels. So here I can actually pull up an example here. So this, let me switch my share. So this is an example of 7 feet of water level, which is that very high end of a moderate emission scenario beyond 2100, or what you might get for a more modest sea level rise on top of a storm. So here we're looking at some of these cities, and you can see, yeah, this is 7 feet is a lot. If we go and try, say, 3 feet, here we go, turn off 7 feet. You can see, right, that's sort of more potentially manageable if you don't have a flood overcoming it. The thing to realize about barrier islands is they're barrier islands for a reason. They don't actually want to stay in place. If you let them move, they're going to try to move. And so beach replenishment is already a core solution, sort of keeping these islands in place when they're inhabited. So we're dumping a whole lot of sand on those, and that's sort of essential for people to be able to live on that. And that can carry on for a certain amount, and how far that can carry on is something that you sort of have to go in and look at very, very locally. But it's I think that I don't have a good pat answer for this, except to say, like, if you're a shore community or you're a coastal community on a river, the Delaware River, say, you better be looking at these maps and thinking about what you're going to do with sea level rise hits when sea level rise hits 2 feet, when it hits 4 feet, which maybe it won't in this century, but will in the next. If it hits 7 feet, like this contingency planning is really important.
Another question was whether fracking is contributing to the problem.
I think there's two answers to that. Well, fracking is a way of extracting fossil fuels, and fossil fuels are driving the expansion of the ocean and ice mass loss. So from that perspective, yeah, it's everything that produces CO2 is part of it. The only way to stabilize global average temperature, and in the longer run to stabilize global average sea level, is to get greenhouse gas emissions to net zero. I'm not sure I said that in this talk, but this is a really important point that I hope you take home. Right? The climate is going to keep changing so long as we're dumping carbon dioxide into the atmosphere. The only way to get the climate to stabilize is to get global carbon dioxide emissions net zero, meaning if we're still putting CO2 in the atmosphere, we have to be actively removing an equal amount. In terms of sort of local effects, if you were fracking in a coastal area, it would contribute to subsidence. There is no fracking in the Jersey Shore or in most of the coastal communities in the Atlantic coast. The Gulf Coast, in the Gulf Coast, oil pumping of hydrocarbons out of the ground, not fracking, just pumping hydrocarbons out of the ground, just like pumping groundwater out of the ground, is causing a significant amount of subsidence. Yeah.
So a follow-up related question was, someone said building high seawalls and demanding residents move inland, since that isn't going to stem the problem on both coasts. So aside from changing carbon dioxide production on a global scale, what kinds of sustainable deep ocean solutions to sea level rise do you know about that would potentially help prevent massive destruction and not just erosion of our coastal areas?
I think I gave you the toolkit, right? So the global carbon dioxide emissions and global greenhouse gas emissions reductions are a core one. And then locally, right? You've got nature-based solutions that can help dampen wave energy. You've got things like beach replenishment and dune construction that can help, again, block water coming in. And you've got various sorts of accommodations so that if it floods more frequently, you can deal with that. But there's no magic bullet here, right? The sea level is rising. We've got to deal with it at a local level and deal with the driver, which is largely and increasingly global climate change driven by greenhouse gas emissions.
So the next question was a little bit more about storm impact. Do return interval for storms, for example, 50-year storms, need to be revised or replaced with another system of describing storm strength and probability to accurately reflect actual risk to coastal properties?
Yeah, well, so one thing I think I successfully avoided. I don't tend to use return periods because people find them confusing. They think often think if you have a 10-year flood, you're not going to get another one for another 10 years. When that's not what it means. What it means is that there is a 1 in 10 year chance, 1 in 10 chance per year. So if you have a 10-year flood, there's still a 10% chance you're going to get another one next year. So one, I would just move away from talking about return periods and frame them in terms of the annual chance. Now, the other thing is that the way we tend to estimate annual chances is by looking at the historical record, and that is changing. And so what you have to do is talk about it with respect to the chance in a particular year or over a particular period of time. So I think you can still talk about the probability of flooding, but yeah, probability of flooding, a 1 in 10 year flood in 2020 is not the same as a 1 in 20 year flood in 2050.
What role does shoreline hardening play in the battle against sea level rise?
So, I mean, I think this may have come before I got to the part where you talked about, but that's one of the things in the toolkit. And I think that the hard protective infrastructures and hardening, I mean, you could use it to mean, things like seawalls, things like beach replenishment is not really a nature-based solution. So it's sometimes lumped in here too, if you just broadly refer to the sort of things the Army Corps does most of the time as hardening. But yeah, that is a core solution. You're not going to say build a seawall around a barrier island. That just doesn't work. But you can use seawalls to protect inland areas, and that's, if you have a place like Manhattan where there's a large concentration of people and a large concentration of property, you're probably going to have to do quite a bit of that.
One person, this seems like another sort of mitigation factor possibility. How much do white, highly reflective roofs help?
White roofs. So about 10 years ago, I worked at the Department of Energy, and this was something that Steve Chu, the secretary, was very enthusiastic about. They help in, they're not a huge solution, but they help in a couple of ways. So one is that they reduce energy consumption for cooling. And there's a little bit of a trade-off there because they increase energy consumption for heating, but in the long term, for most of the world, including increasingly this area, the cooling demand is going up faster than heating demand is decreasing. So they help reduce. They're an energy efficiency measure that reduces demand, and they also very slightly increase how much light the planet reflects away, and so have a very small global effect. But that's a quite small global effect. There was a paper I read 15 years ago that did the calculation. It's on the order of 1/100 of a degree if you had a lot of roofs globally. But the effect on individual houses and also potentially the effects on urban heat islands can be larger than that, or are larger than that.
So one person brought up what's been talked about, which is even though there's been a decline in emissions during COVID, is it true there's still approximately 410 particles per million remaining in the atmosphere?
Not only are there still 410, there's more than that. right? I mean, the thing right, the carbon dioxide accumulates in the atmosphere. It comes out quite slowly, right? So reduction in emissions just means we're putting a little bit less, about, I think it's 7 or 8% less in this year than we did last year. So carbon dioxide is still going up at almost the same rate as it went up last year, just a little bit slower. And so I think we're around 414 parts per million now.
Do your high-end projections factor in extreme tipping point events like release of some suboceanic methane?
So I would say yes and no. The high emission scenario, the way it's formally done is sort of is constructed assuming, basically fossil fuel use continuing to grow the way it was growing in the 2000s and well, it was growing in the 2000s, so that you end up with basically double current fossil fuel emissions by around 2060. That's not the policy trajectory we're on now. So to get onto that high emissions trajectory, you need to you would need to have some feedbacks that are not well represented in climate models. So I would say the high end scenario is probably higher even than you would be able to when you would likely push emissions with those feedbacks, but some sort of feedback producing more emissions than we think is currently likely would be what the sort of thing that might get you onto that high end trajectory, even as market forces and policies are starting to level off emissions.
Here's a non-technical question for you, but to the point of how do you make non-believers believe? And the person asking said, I'm thinking of all the deniers.
So I'm going to just channel my colleague, Katharine Hayhoe, who speaks much better on this than I do, and encourage you to go look for some of her talks. Katharine is an amazing woman who is a climate scientist at Texas Tech and is also evangelical Christian. And because she's an evangelical Christian and ended up in Texas over the last decade plus, this sort of interface has become her thing. But what she would say is a couple of things. So one, there is a fraction of the US population that is sort of a hardcore denier, but it's only about 10% if you look at some of the Yale studies. And there's another 15% or so which is sort of leans that way. It's about 60% of Americans are concerned or very concerned about climate change. So to some extent, they say, like, I wouldn't worry about the 10%. And I would also say that if you're thinking about this, you should just think about the current pandemic experience and how you think about skeptics in the context of the pandemic. I think everybody has gotten a lot more experience with these sorts of questions over the last 10 months. But in general, like, you could say, okay, well, she would start by connecting to people where they are, connect to them as people, talk about solutions. Don't start, I sort of went in with this talk and said, like, here's the problem, here's the science. That's not how one would give a talk if you were speaking to an audience that wasn't receptive to it. I probably would not be the right messenger for that sort of audience. I'm a secular Jew I'm probably not going into talking to a bunch of conservative evangelicals who think the Pope is too liberal because of his climate work. I'm not the right person to talk to them. But the basics are, is you connect to people as people. You listen to them. Like the same thing. I don't need to convince people on climate change. But if you're having a discussion about the future of a community, like, that's something where it's no longer a black and white issue. Yes, climate change is real. The science is well established, but what you do as a community is something that's a hard conversation anyway. And I think that's, active listening, developing trust, like, those are all the sorts of things. I think it's very hard to do this on a one-off, and you really have to build relationships. And I alluded to the idea that there are boundary organizations. There are people whose expertise is working on this interface. Like, that's really important. I think sustained relationships and sustained listening is ultimately, I think, what has to happen there. And I in terms of the big global mitigation policy, I wouldn't worry about the 10% any more than I would worry about the 10% who are, hardcore mask deniers.
Any governmental or private sector entities, either in the US or beyond, that you know of that are currently using the flexible adaptation pathway approach to create their plans?
Yeah, so a lot of this work has been done in the Netherlands as part of the work by the Delta Commission. And they have some great people there. There's been some work in Australia and New Zealand as well. It is recommended in California state guidance, but I actually haven't seen that many implementations. And the thinking behind this is starting to seep into things like Army Corps plans. So like the Army Corps Jamaica Bay study has technical triggers. So like when sea level gets to 1 feet, you're supposed to implement this. What I think that it still needs a lot of work, though, is it sort of has a community, is a participatory community tool. I think that I haven't seen that much. I mean, so the idea of the flexible contingency pathway, I think, is largely driven by a very engineering focused view at the moment, which may be easier to do, but ultimately we really need to have community dialogues and integrate this approach into there. And I'm hoping we can facilitate more of those in New Jersey.
Do you have any projections for intrusion of salt water up the Delaware River as a result of Atlantic sea level rise, and how that might affect drinking water from the river, that the river systems use for Southeast Pennsylvania? This question was specific.
So I do not. I am, however, tomorrow morning speaking to the Delaware River Basin Commission on sea level rise projections, and they have a project to look at this.
Okay, so we will await the results of that conversation, which there's still lots of questions. So trying to
thank you. I see some people leaving there. I say thank you everybody for coming. It's been a lot of fun.
Does resilience policy plan for mitigation of ecosystem destruction, or primarily, I guess, focus on human infrastructure?
I think it depends, but there certainly is efforts that focused on ecosystem preservation, and groups like the Nature Conservancy think a lot about this. And there's also, as I alluded, there's a lot of work on trying to work with nature to reduce some storm impacts as well.
This question is, have you worked on interior land interventions to the sea, so river, lake, stream, to the sea level issues?
I've not. There's been one of the on the more people who do sort of engineering studies, there's one of the interaction of sort of river and flooding and coastal flooding, and for them to matter stormwater flooding by sewers, is a really important area of research and a pretty active area of research. But I'm not an engineer. I talk to the engineers, and it's more their sort of domain. So there's been some work by colleagues at Rutgers and also by colleagues at Stevens that I know of locally in this area.
So I'll just also say for everyone, and they may know this, but there's also a lot of really interesting comments and a little chat going on between people. And I'm trying to pitch the questions to you first. But for people who are interested, there's some really nice conversation happening in the chat as well. This question, private interests, public interests, and environmental interests seem to be at odds when it comes to how to address sea level rise. Do you have any advice for how public servants working in local government can protect vital habitats and the threatened species that depend on them in a political atmosphere where private property rights tend to prevail?
I think that is an excellent question and really pushing the bounds of my expertise. I'm a climate scientist who is increasingly into this sort of areas of social science and law and policy, but I think it's a really great question. And I don't think I'm going to freelance here and try to answer it. it's complicated. I would say not only are they complicated, there's actually a pretty thin literature in the academic literature on sort of the politics of coastal adaptation. I have a thesis advisee who just successfully defended at Princeton, DJ Rasmussen, and who did a variety of stuff. And one chapter of his was trying to look at some historical case studies of the politics of building coastal flood protection infrastructure. And there's not a lot, and he had to do a lot of original archive work, but I think it's a really interesting area.
And there was a couple people who just said, get involved in local politics and community action and vote, all those things that can have an impact. One person asks, a couple of people are interested in sort of projections about sea level rise and asked if you have a map or I guess a visualization of, I'm trying to find this question, so people could see the impact of flooding.
Yeah, so njfloodmapper.org, that's a Rutgers tool. Sealevel.climatecentral.org is another one that has sort of a national scope by another set of collaborators. NOAA has some that the NJ Flood Mapper is an extension of. But if you're in New Jersey, njfloodmapper.org, more broadly, sealevel.climatecentral.org have good tools.
Are you aware of any serious legislative efforts to reduce the inappropriate incentives that you mentioned for development of flood-prone areas brought about by governmental flood insurance or disaster relief?
Yes. A few things. Well, so one, there was originally an attempt to make the National Flood Insurance Program offer actuarially sound rates, and it got, and I'm blanking for whatever reason on the bill, but once the rates started rising, it got rolled back or at least postponed. And partly that's a really legitimate concern because these are not all, because it disproportionately affects lower income population. The National Flood Insurance Program is capped at 250,000 anyways. So you have to give careful attention to the equity issues involved. I think the original, I think it was Big Waters, if I'm remembering right, may not have done that fully. But the sort of dealing with the soundness of the National Flood Insurance Program is one thing. There are efforts to put more money into pre-disaster mitigation right now. The way disaster recovery funds normally work, it's hard for community to get money to invest in making themselves more resilient until after there's a disaster. And so thinking about that is another thing. The Obama administration had a flood standard that was incorporating sea level rise into federal planning that got rolled back by this administration, but I assume it was executive order, I assume will be restored promptly. So there is a bunch, but it's challenging, and there's also a lot of equity and justice issues wrapped up in how disaster recovery funds are awarded. And there's also, frankly, right now, like, you just have to look at the past few years, there are a lot of examples of disaster recovery fund, so there are some things like the National Flood Insurance Program, which just runs, and it has some structural financial issues. There are other things like large scale disaster relief, which require congressional action. And those, as with everything congressionally, those wheels have just been getting slower and slower, right? Every time there's a large disaster now, funds are held up for months because of some internal congressional politics or other. And you saw how long it took to get relief funding to Puerto Rico after Hurricane Maria, for example. But even with Hurricane Sandy, there was a couple months delay. I mean, there are. I had a column in the Star Ledger in October that and this is maybe a slightly depressing, but a slightly optimistic note to end. And like fundamentally, a lot of these challenges are really governance challenges, which means to address them, we have to deal with some of the structural challenges of our democracy not necessarily working as well as it used to. That's, I'm a climate scientist. I wish this were a technical problem, but really it's not. It's a governance problem, and there are so many domains of life in our country that are being touched by failures of governance, particularly at a national level. And like addressing those is sort of, I think, probably the single most important thing we can do to resolve a lot of these issues.
That seems like a great way to wrap up. And it's just before 8, and I know you want to walk your dog and have dinner. But I want to thank you. And I will say that a lot of the people on the chat want to thank you too. They said it was a wonderful presentation, learned a lot. We are so thankful to have had you, Bob, for this last presentation of our year. And it was fascinating. We had tons of people, and we hope to see everyone again. We wish everyone happy holidays, great end of the year. And let's hope we can control our sea level rise in the future. So thanks and good night, everyone. And please join us in 2021.